Okay.
Okay, so hello everybody. Allow me to please extend a very warm welcome to Valeria Villani. She's an assistant professor from the Department of Sciences and Methods for Engineering at the University of Modena and Reggio Emilia in Italy. So her research interests really align very closely with our lab. So she focuses on the design of human-centered user interfaces for efficient cooperation between humans and industrial machines or robots. Again, very multidisciplinary. And today she'll be talking about her anthropocentric framework for intuitive human-robot interaction. So thank you very much, Valeria.
Okay. Thank you so much for the introduction and above all for the invitation, because it's a great pleasure for me to be, here and at least to be talking to you and meeting you all. So I hope you can see my PowerPoint presentation mode screen.
Yes, it's fine.
And if I go to the second slide, you can see it, right?
Yes, we can.
Okay, perfect. So it should work. So thank you so much again. And as it was announced, I'm from Italy, and mostly, as you can hear from my accent. And in particular, I come from the University of Modena and Reggio Emilia, which is located in the Emilia-Romagna region, here the blue one, and it's a university located across the two cities of Modena and Reggio Emilia. And it's the area where Ferrari cars are produced and where we have Parmesan cheese and balsamic vinegar and also Maserati and Ducati and Lamborghini cars. So it's a very nice area where to live, and also it's a highly productive area. And in particular, I'm from the Department of Engineering in Reggio Emilia, which is the one on the left. And just nice to say that it's the third most ancient university in Italy, and since it has a long history. And the lab where I work is called Arts Control, and so we mainly work with in the fields of automation and robotics, and in particular dealing with control problems. So with the control of automatic and robotic systems. And the lab was started almost 20 years, and actually it's we are fluctuating, but actually it's not 30 people. If we consider students working with us, we are much more, and the picture is quite old. So and we have also a startup company which is called Industria Tecnologica Italiana, and its main goal is that of, let's say, translating into practice the research problems we deal with at the lab. As I said, our activities are mainly in the domain of automation and robotics, and in these two domains we span across a large different variety of activities. So we deal with different problems, and in particular I'm focused on the interaction with such systems. So either in the automation and in robotics field, I'm focused on studying how human gets interacting with such systems. And I would like just to show you a quick video about our lab, so you can have an overview of the activities we are working with, and then we can go into the detail about the presentation. So. So I think that once is enough. Okay, so then about me, I mean, I mentioned before that I'm involved in, I'm interested in studying human-machine and human-robot interaction, basically because I mean, my scientific background is in biomedical engineering, and in particular, I had a PhD on biomedical signal processing, and I'm sort of leveraging my background and putting in the fields of interaction systems in order to provide a human-centered view of the interaction and what is required by the human user in order to have, let's say, an easy interaction with complex system. And why is it important? Basically, I mean, when we are talking about interaction systems, of course, studying and optimizing the way these systems work is fundamental, but it is important also to focus also on the interaction related aspects, and in particular, if the interaction with such systems is poor, then we have a certain number of drawbacks, basically because I mean, we are introducing a sort of barrier to the use and the introduction of these systems, and the performance of interaction decrease when the interaction means are not properly studied and tailored on the user. And what happens is that typically, only expert users can use such systems. So we are preventing non-expert users from the use of any complex system or technologically advanced system. And even those users who can use such systems, they have, let's say, a bad feeling, a bad perception of the technology in general. So we are negatively affecting user satisfaction towards technology. So this is, let's say, a general motivation to the importance of making the interaction with robots and with complex systems intuitive. And how can we achieve that? Basically, we can think about 4 different methods to achieve this. First one is related to programming. So finding some easy ways to program such systems, and in particular to program robots, so that not advanced programming skills are required. And it's, for example, the case of learning by demonstration for robots, where you simply show the robot what you expect it to do, and you physically show it without the need to program it in robot programming language. And apart from programming, then we can focus on the way humans communicate with such systems. So in particular, how they exchange inputs and outputs towards the robot. And additionally, another approach, or another complementary approach to make interaction intuitive, is providing adaptive interaction, so customizing robots or the system's behavior to the capabilities and the current status of the user. And if this is not enough, we can also exploit reality enhancement methods such as virtual reality or augmented reality in order to provide additional information to help the user during the interaction. So in the presentation, I will go through I will not talk about programming approaches for intuitive interaction, and I will present some of our results about the second, third, and fourth approach. So let's start from the use of intuitive modes for input and output exchange between human and robot or an automatic machine. let's say from one side we have the user, and at the other side we might have either a robot or a machine, or in general any technologically complex system. So examples of examples of methods to provide inputs and communicate with robots intuitively can be the use of gestures, the use of vocal commands, and also eye tracking and facial expressions and so on. And all these methods have been widely proposed in the literature and are quite, let's say, established methods to interact intuitively with robots, and avoiding the bottleneck related to the use of a mouse and a keyboard, and again, programming language and other not so user-friendly interaction modes. And in particular, in this field, we have proposed a method that is based on gestures, so gesture-based interaction approach. And in particular, we have integrated in it the two important concepts of interaction, which are natural and tangible user interfaces. So basically the idea is that, okay, we want to find a way to interact with robots that is intuitive. How can we achieve this? Let's think about a natural user interface, which is a user interface that actually exploits our knowledge of everyday words and implements a direct expression of our mental concepts. And let's use also a user interface that is tangible, in the sense that it acts in the world where the robot is and where the user is located. So in particular, our approach relies on simply on the use of a smartwatch, or in general of let's say commercial device that is worn by the user at their wrist and tracks wrist movements. These movements can be properly processed by a sort of control architecture, and specific movements of the user can be translated into commands for motion control of any kind of robot. So let's see some general features of this architecture and then some examples. As I said, we are considering the use of, I mentioned a smartwatch, but in general, any commercial device that is not developed ad hoc for interacting with robots. So we focused on a commercial multi-purpose device, such as a smartwatch or any bracelet for activity tracking, which mounts an inertial magnetic unit. And as a result, we can achieve an infrastructure-less interaction, in the sense that we don't need cameras, we don't need any ad hoc device, and also the interaction that we achieve is hands-free, in the sense that the user doesn't have to hold anything in their hand. And in particular, if we use a smartwatch, then we can have two additional features, which are haptic feedback, basically in sense of vibration. And we can exploit the smartwatch or the bracelet heart rate sensor, which can be useful, as we will see later, for adaptive interaction. And a nice feature of this approach is that it's general. I mean, provided that we have a device like this one, then, and provided that we properly configure the control architecture, then it can be used to interact with almost any kind of robot. And we will see some examples in this regard. Okay, so these are some general features, and let's see how the approach can work. I mean, how can we translate movements of the user into commands for the robots? As I said, we wanted to create a natural interface. That means that we wanted a natural mapping of the movements of the user, of the 4R movements, into velocity commands. So basically turning rotating wrist towards left means that implies that the robot will go left, and as well right, and back and forth. So basically something quite natural, where human movements are clearly mapped into resulting movement for the robot. And this can be used, as you can see in the video, to, let's say, teleoperate the robot. So my movements, that's my wrist, my movements are directly mapped into movements for the robot. But in addition, we added some gestures, so some discrete gestures that can be used for imposing high-level commands to the robot. So for telling the robot to start a predefined command. And in particular, we defined 5 gestures, which are this one, and okay, so a sharp movement towards up, down, left, right, and a circular movement. And when these gestures are performed, they are linked they are translated as to an high-level command for the robot. For example, a sharp movement towards up might imply for a drone, if we are interacting with a drone, that we are telling the drone to take off. And as well, a sharp movement towards down implies that the drone should land. So stuff like that. I mean, these are predefined behavior for the robot, but again, we try to associate these gestures to have a natural mapping with the associated behaviors of the robot. So the general architecture for this approach is that, I mean, the robot starts from an autonomous state, initially is in an autonomous state, and then we can use gestures to move the robot across different states. And if, for example, autonomous at the beginning is just that the robot is stopped and is not moving, by using a gesture, we move the robot in a different state where it is supervised, so when the interaction with the user starts. And for example, to achieve, to get to the teleoperation, the one with natural mapping that we saw before, then we use another gesture, and the robot is led to teleoperation. And we test this system with different robots, basically because, I mean, this is the general architecture, and depending on the gestures you select and the different status you select, you can customize this architecture to the robot under consideration. And for example, in the case of the drone, then we used the up and down gestures for landing and taking off. And of course, this didn't apply to the case of a wheeled robot. And then in this case, we had simply the teleoperation state, since the robot was moving on the ground. So this is a first approach for natural interaction, and it falls in the case of providing input in a natural way to the robot. I mentioned before that using the smartwatch and its vibration can also be useful for providing haptic feedback, so for receiving outputs from the robots. I didn't put slides in here in order to get not too much long, but using the vibration provided by the smartwatch allows to get some basic information from the robot to the user. And for example, a basic use of haptic feedback is about recognition of a gesture. So the user performs a gesture and the robot informs the user if the gesture has been recognized by providing a short vibration boost to the user. So we can, by working on vibration feedback and improving the patterns of vibrations that we provide to the user, we can establish an improved communication also from the robot to the user. So we have a sort of bidirectional communication between the user and the robot. From the user to the robot is basically in terms of motion commands, either in teleoperation state or by using gestures. And from the robot to the user, then we can, by using vibration feedback, we can provide information about the status of the robot, about possible presence of obstacles, and about the recognition of the gesture, as I mentioned before. So this was a first step towards the goal of achieving an intuitive interaction with robots. And then the step that came after was that, okay, can we do something more? And in particular, can we think of customizing the interaction depending on users' behavior, just like humans do when they interact and collaborate among themselves. Just for example, if I'm doing something, if I'm working at a task with a colleague and I'm suddenly getting tired and I'm overloaded with the task, then what good colleagues typically do is that of taking more charge of the task and letting me relieve and gain some more energies in order for me to get back to my usual working condition. Then the idea was that of trying to replicate this approach and this way to interact that humans have among themselves to the robot in order to provide an adaptive interaction. So this problem can be formalized by requiring that depending on the workload of the user, or depending on the emotions of the user, so depending in general on the status of the user, we would like that the robot is able to recognize different status and to achieve a different level of autonomy in order to help the user when the workload gets too much. So this was the general problem, and in particular we implemented this a possible solution to this general problem, to this goal, by creating these we call them mate systems, in the sense that they are systems, either automatic or robotic systems, that are able to measure human capabilities and adapt the interaction accordingly. And if the adaptation of the interaction is not enough, Then they provide the user with additional training and support depending on the application scenarios. So in order to adapt the interaction, of course, we need to know, we need to measure what is the current user status and what are users' capabilities. And based on this information, we can adapt the interaction and, if necessary, provide some additional support. This approach falls into the field of affective robotics, which basically consists in enhancing the interaction of a human with a robot by recognizing users' affect. So in general, either emotions or workload or fatigue. And the nice aspect of affective robotics is that we can provide, we can collect some implicit feedback about the interaction without asking the user how he or she is perceiving the interaction, but simply measuring some, in particular, some physiological signals related to that are indices of users' affect and emotions. And as a result, the behavior of the robot can be adapted accordingly to this implicit feedback we are measuring from the user. And in particular, in our considering our goal, we can change the level of autonomy of the robot in the case that some increased workload for the user is detected, in order to let the user be able to relieve and get back to the initial mental status. In particular, the approaches based on affective robotics in general consider users' emotions and a wide range of users' emotions, and we just focused on measuring cognitive workload, basically because we were targeting working scenarios and where the cognitive workload is the feature of the user that is most important to track and to estimate. So our approach, what I'm going to show you in the next slide, is focused on the measurement of cognitive workload in order to implement these MATE systems, measure, adapt, and teach systems. But of course, provided that you are able to measure other emotions and the general affect of the user, the approach can be generalized to take into account indeed other conditions and other emotions of the user. So going back to the architecture that I showed you at the beginning, the one that I showed is in this green. So we said before, we have the user that is wearing a smartwatch, and we provide some the quantities measured by the smartwatch become some control inputs that are processed by an architecture and determine some velocity commands for the robot, and also information from the robot can be provided back to the control architecture and to the user. So the one in green is what I showed you before, for example, in the gesture-based interaction approach. And if we want to provide some adaptive interaction, the green part is enhanced with the blue parts, or with the blue arrows, where we consider that actually the performance of the user and their capabilities are influenced not only by the robot, but also some external factors, which are some stressors related to the environment and to the user daily condition, let's say. All these stressors or these input to the user determine the mental workload, which becomes an additional variable that we provide to the control architecture. And so the velocity command, or in general the commands that are sent to the robot, depend not only on the inputs provided by the user, but also depend on its mental workload. And accordingly, the interaction can become adaptive. So the mate systems have these three main pillars. And now the goal is that understanding how to implement, how to build each of these pillars in order to make them work in an adaptive fashion. Let's start from the measure pillar. As I said before, the goal of this pillar is that of measuring human capabilities, but in particular measuring the current condition of the user, the current status of the user, and we focused on cognitive workload. We want to measure cognitive workload in an implicit manner, so not asking to the user every 5 minutes, how are you and how do you feel, are you tired? But we want an implicit measurement for cognitive workload. And to this end, we use the heart rate variability, which is a physiological quantity, that is derived from cardiac activity, and it's well known in the literature to as a reliable index for measuring mental fatigue. Then, oh, sorry, I lost, okay. So, in particular, in normal condition, our heart rate typically undergoes some variability, which is, as I said, which is normal. And our heart rate is not constant over time, but even if we are relaxed and in the best of our conditions, then we can measure, it is possible to measure some variability of heart rate. And it is basically due to the interconnection between cardiac and neural system. But what has been observed in the literature for a long time is that in particular cases of mental fatigue, for example, of mental stress, then it is possible to observe some changes to the normal variability of heart rate. So if we study how the variability of heart rate changes over time, it is possible to detect some particular conditions of mental fatigue. And there are some physiological motivations behind that. But what we need to know is that measuring heart rate variability and studying how it varies over time, then it is possible to detect mental fatigue. And I don't know if you're familiar with the concept of heart rate variability, but basically heart rate is measured originally from the ECG or from cardiac activity, and it's the time interval. Heart rate is the time interval that occurs between two consecutive heartbeats. So it's measured from the RR series, where the RR series is the measurement of the RR interval, that is the time occurring between two heart peaks. And heart rate variability is analyzed by measuring different metrics. Basically, they are divided in time domain and frequency domain, and they are very established in the literature. So they are used both in clinical applications and also for physiological studies, and in the case of affective robotics, that is our goal. And as I said, it is possible to observe some variation of these metrics that can be associated to mental fatigue and to states of increased cognitive workload. So basically, if we observe that some of these metrics increase or decrease over time, it implies that the subject under observation is undergoing an increase of cognitive workload or a decrease in cognitive workload. But then our problem is that, okay, I mean, these metrics are well known in the literature, and it is known that how their changes reflect changes in cognitive workload. But then we want to measure heart rate and its variability with a smartwatch, which is a device that provides measurements of heart rate, but actually such measurements are quite noisy and might be affected by movements of the user, since we are measuring heart rate at user's wrist. So we performed some studies in order to verify that using the smartwatch can be a reliable tool for measuring mental fatigue, so that we can include the measurement of mental fatigue in our adaptive interaction framework. And we performed some tests where we exposed the test subjects to some stressors, so to some exercises that are known in the literature to induce stress in subjects. And we measured heart rate during rest condition and during stress, so while the subject was performing this task. And then we analyzed the different metrics for heart rate variability in the two conditions. So we started from the smartwatch, and actually, we could find some sort of differences between the two conditions related to the mean RR, which is one of the metrics used for heart rate variability. So as a first result, we could find that among the different metrics related to heart rate variability, there is at least one that allows to distinguish between rest and mental fatigue. Then we explored further this aspect, and we included also two different devices that are yet commercial, but might be a little bit more accurate than the smartwatch. And these are the thoracic belt and the armband, the thoracic band, sorry, and the armband. And again, we basically performed the same study. And actually, what we found in this study more accurate is that the smartwatch is not that good, but using the thoracic band, it can be, is a proper alternative to the smartwatch. So it is an additional device, but yet it's a commercial device, and it's quite easy to be worn by the user. It doesn't interfere with the user's movement, and we can be pretty sure that it provides accurate measurement of heart rate variability, and thence can be used to monitor mental fatigue of the subject. And so with these studies, we accomplished the measure pillar, in the sense that we proved that heart rate variability is a suitable metric for measuring mental fatigue, but this was known from the literature. And what we proved is that by using a commercial device, an easy-to-wear device, then we can measure mental fatigue indeed. Then the next step is that of adapting the interaction. So adapting the interaction, what does it mean? It means that depending on the human-robot interaction problem or scenario that we have, we should provide some sort of assistive strategies that implement the change of robot autonomy in order to relieve the user while interacting with the system. So such assistive strategies, of course, vary depending on the task and depending on the robot. So they should be devised considering the specific application and the specific robot. And we considered some examples considering different robots, and just to test, I mean, to have some working examples of this approach. And starting with mobile robots, a possible assistive strategy is that of obstacle avoidance, of course, provided that the robot mounts a device, a laser scanner or whatever that is able to recognize obstacles. And in the case of a robot manipulator, then a possible assistive strategy is that of implementing some virtual features that guide the allowed movements of the user. I won't go through the details of the experiments. And in the case of collaborative robots, working together with the user at a collaborative task, then a possible adaptation of robot behavior is a possible assistive strategy is that of varying the allocation of tasks between the user and the robot in order to create a sort of job rotation and allow the user to get, let's say, less bored with this working task. In the case of multi-robot system, a simple assistive strategy that we used was based on consensus, so simplifying the robot's movements in the case of mental fatigue of the user. And then we have the third pillar, which is the one about, which is about the one about teaching or providing further support to the user in the case that the adaptive interaction is not enough or the user is completely new to the interaction task and the interaction device. And I mentioned it at the beginning, to provide additional support to the user, then we consider the use of reality enhancement techniques, so basically virtual reality and augmented reality, as a ways for the user to have additional information about the reality and about the interaction task, either offline, so before starting the task, which is the case of virtual reality, or in real time, which is the case of augmented reality. So in particular, in this slide, you can see an example of virtual reality as a teaching tool in order to let the user become familiar with a complex interaction scenario and a complex interaction task, and also a novel interaction means that is the one based on the smartwatch that I presented at the beginning. So using virtual reality, we can build complex environments, complex tasks, and we can let the user get familiar with the task that is going to perform in the real environment. So this was quite a quick overview of these mate systems, basically considering the case of the interaction with robots. But we applied the same the same framework, let's say, considering industrial automation, so industrial machines, where, of course, the interaction task, the kind of interaction that involves the user is quite different, because we have, in the case of industrial machines, we typically have user interfaces and some physical buttons mounted over the machine, and the interaction occurs mainly through user interfaces. But nevertheless, it is possible to implement the same approach, to customize the same approach, considering such systems. And in particular, it's something that it's that is getting quite, let's say, popular under the requirement of Industry 4.0 and 5.0, where again the focus on the on workers and on the manpower getting back to industries. So I will show just a couple of videos showing the application of such made systems in industrial automation. This work was performed under during a European project that finished almost 1 year ago or something more, and it was called Inclusive. So the goal of the project was that of devising smart and adaptive interfaces for inclusive work environment. So I will show you an introductory video to the project, and then a video about the results that we achieved within the project.
Production systems are increasingly complex in order to meet the challenges of the market. As a consequence, human-machine interfaces become crucial in machine performances. Operators with different skills, cultural backgrounds, and cognitive capabilities might take great advantage by personalized interfaces. Inclusive drives a new concept of interaction in which the perceived behavior of the automation system adapts to human capabilities and not vice versa. Measure, adapt, and train are the key words of inclusive research. Inclusive team involve directly operators from real industrial use cases, representative of broad industrial scenarios, to develop human-machine interface system able to measure the sustainable cognitive load of the human operator and capabilities to accomplish automation tasks in cooperation with the production system. Adapt the automation functions and the information load of the production system to the measured capability of the user. Train and support operators to accomplish a complex automation task, properly integrating a virtual environment and an industrial social network. Inclusive is the answer for advanced manufacturing industries which aspire to increased human and automation performance, customized products, workers' satisfaction.
Okay. So just a few comments about the video, and as you saw again the three pillars of the system. So measure, again, adapt and teach. In particular, these were implemented as regards the measurement. We had a more complete measurement of human capabilities, considering not only cognitive effort, but also constitutional skills, physical effort, and performance. And then the adaptation part was tailored, considering that the presence of user interfaces, so graphical user interfaces, And as regards the teach system, we had an offline virtual training based on virtual reality and an online speech-based system based on augmented reality. So we had a more complete framework of made systems. And we had 3 different use cases. I will just show you a video about the first one, which is about the production of machineries for woodworking. And here is the video. So here, basically, the assistance or the task that involves the user is related to the configuration of the machine, and the user is guided in the configuration of this machine, and the adapt and teach modules are implemented regarding this task, just so providing guidance to the user depending on the output of the measured module, and providing instructions as regards to the teach system for these tasks, so for the configuration of the machine. And I think we can skip the end of the video. So basically, this was a quick overview of my recent works. And of course, we have some ongoing research. I mean, building upon what we have done so far, and trying to extend our results, and working also with psychologists from our university in order to understand more deeper what is people's attitude towards robots, whether they perceive them as collaborators or antagonists, and so on. So let me conclude my my presentation, and hopefully, I think probably I went too long, so I apologize for that. And I don't know if we have some time for questions, if you have any. I can stay longer than now. It's 9.
Oh, thank you so much. This was a really